Hi, welcome to our CompTIA Network Plus course. In this lesson, we will talk about the OSI reference model, and we will cover the following topics such as the physical layer, what is the data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. The OSI reference model is a conceptual framework for understanding network interactions. It standardizes networking protocols and ensures interoperability between diverse systems. This lesson explores the 7 layers of the OSI model and their practical applications in modern networking. The Open Systems Interconnection, or the OSI reference model, is a conceptual framework that provides a standardized way to understand and describe how networks communicate. It is a 7-layer model, and each layer is responsible for specific functions and protocols. The OSI model serves as a blueprint for network engineers, developers, and administrators, ensuring compatibility and interoperability between diverse networking systems. The OSI model is a layered architecture dividing network communication into 7 distinct layers, and each layer performs a specific tasks, building upon the services provided by the layer below it. This layered approach simplifies network design, troubleshooting, and implementation. Standardization is utmost in networking, and it ensures that different devices and software from various vendors can seamlessly communicate with each other. The OSI model promotes interoperability, allowing networks to be built using components from different manufacturers, creating a diverse and robust ecosystem. As I've said earlier, each layer has a specific function and protocol working together to enable end-to-end communication across networks. For example, the physical layer deals with the physical transmission of data over a medium like a cable, while the application layer handles interactions with user applications. Let's talk about the first layer, which is layer 1, or the physical layer. The physical layer is the foundation of network communication. It deals with the transmission of raw data bits over physical media. This layer defines hardware specifications for devices, transmission media, and electrical or optical signals. Think of it as the plumbing of a network, ensuring the physical connection and flow of data bits. Now consider a simple example, like connecting your computer to the internet via an Ethernet cable. So the physical layer dictates the cable's type, like is it a Cat5e, Cat6, with an RJ45 connector type, and the voltage levels used for data transmission. This layer is responsible for ensuring that the data bits are transmitted accurately across the cable. Now, the physical layer defines the physical media, right, used for data transmission, such as copper cable, like coaxial twisted pair, fiber optic cables, and wireless signals. And each medium has a different characteristics in terms of bandwidth, distance, interference, susceptibility, and cost. Now, in terms of signal encoding, the physical layer specifies the encoding schemes used to represent data bits as electrical or optical signals. And these schemes determine how data is translated into physical signals and back again, ensuring accurate and reliable data transmission. Now, network interface cards, or what we call as NICs, or network adapters, are essential components that connect devices to the network at the physical layer. These cards translate data bits into electrical or optical signals and vice versa, facilitating communication with other devices on the network. Signal timing. The physical layer specifies the timing and synchronization of signals, ensuring that devices on the network can transmit and receive data at the correct rate. This includes defining clock signals and synchronizing data transfers to prevent data loss or corruption. Now let's talk about the second layer, or what we call as the data link layer. The data link layer bridges the gap between the physical layer's raw bit transmission and the higher layer's more abstract data handling. It provides a reliable and efficient means of transmitting data between directly connected network devices. Now, by managing data framing, addressing, and error control, the data link layer ensures that data is delivered to the intended recipient with minimal errors. Notable protocols operating at this layer include Ethernet. Let's put it here, Ethernet, which is the most widely used networking technology. We have PPP, point-to-point protocol, commonly used for dial-up connections. Like in 20 years ago, this is very popular. And it's used for connecting remote devices to a network. And these protocols define the format of data frames, addressing schemes and error control mechanisms, providing a robust foundation for network communication. Let's talk about the first concept, which is data framing. The data link layer is responsible for organizing data into frames, adding headers and trailers to each frame. These frames contain information like the source and destination source and destination MAC addresses, error detection codes, and other control information. And this ensures that data is transmitted and received reliably between network nodes. Then you have the media access control, or the MAC. MAC addresses are unique identifiers assigned to network devices. The data link layer uses MAC address to control access to the shared network medium. For example, in Ethernet networks, MAC addresses are used to ensure that only one device transmits data at a time and preventing collisions and ensuring efficient data flow. Third concept is error detection and correction. The data link layer implements mechanisms to detect and correct errors that may occur during data transmission. It uses error detection codes like CRC or the cyclic redundancy check to verify data integrity. If errors are detected, the data link layer can request retransmission of the affected data, ensuring reliable data transfer. Let's talk about the third layer, which is the network layer. It is responsible for managing the flow of data packets across different networks. It operates above the data link layer, which handles local communication, and below the transport layer, which ensures reliable end-to-end delivery. The network layer is the backbone of internet connection, enabling devices on different networks to seamlessly exchange data. Let's talk about the different concepts. We have packet routing. So at the heart of the network layer is packet routing. It determines the optimal path for data packets to travel from source to destination, navigating through complex networks with multiple nodes and connections. Packet count routing algorithms analyze network topology, traffic patterns, and network conditions to identify the most efficient route for data transmission. This ensures that packets reach their destination quickly and reliably, avoiding congestion and delays. Now, the network layer uses logical addresses to identify devices on the network. The most widely used addressing scheme is Internet Protocol, or IP, which assigns unique IP addresses to devices and enabling them to communicate with each other. IPv4, which is the older version, uses 32-bit addresses, while IPv6, it uses 128-bit addresses, providing a much larger address space to accommodate the ever-growing internet. Now, the network layer manages various protocols that is important for network communication, including IP. You got ICMP, which is used in ping, and ARP, which is Address Resolution Protocol. IP handles addressing and routing. ICMP facilitates error messages and network diagnostics. And you have ARP, which resolves logical IP addresses to physical MAC addresses for communication between devices on the same network. So I'm just going to put it here. So you have the IP, you have ICMP, then you have ARP. Okay. Fourth concept is network segmentation. The network layer enables network segmentation, dividing a large network into smaller subnetworks. This improves performance, security, and manageability. Routers, devices operating at the network layer, act as a gateway between subnetworks, controlling data flow and enforcing security policies. Network segmentation allows for efficient resource allocation, reduces broadcast traffic, and isolates different parts of the network, enhancing security and stability. Now let's talk about the fourth layer, or what we call as the transport layer. Here, we typically talk about two different protocols, which is TCP and UDP. So what are those? So TCP, or the Transmission Control Protocol, is a connection-oriented protocol, meaning it establishes a virtual circuit between the sender and the receiver before transmitting data. Now, this connection ensures reliable delivery, guaranteeing that all data packets arrive in the correct order and without loss. TCP handles error detection and retransmission, ensuring data integrity and completeness, and it's often used for applications requiring high reliability such as web browsing, email, and file transfers. Now, the second concept, or the second protocol, is UDP, or the User Datagram Protocol. The User Datagram Protocol is a connectionless protocol, meaning it doesn't establish a connection before sending data. It offers faster data transmission with less overhead, but it doesn't guarantee delivery or order. UDP is often used for applications where speed and efficiency are critical and some data loss is acceptable, such as streaming video, online gaming, and voice communication. UDP is also used for DNS queries, which are often time sensitive. Now, what are the key differences between the TCP and UDP? So the primary difference between TCP and UDP lies in their connection-oriented and connectionless nature. TCP prioritizes reliability and guaranteed delivery, while UDP prioritizes speed and efficiency. TCP is slower, right, due to its connection setup, error checking, and retransmission mechanism, while UDP, in contrast, is faster because it doesn't establish a connection or perform error checking, leading to less overhead and faster data transmission. Let's talk about the fifth layer, which is what we call as the session layer. The session layer is responsible for establishing, managing, and terminating communication sessions between applications. It sits above the transport layer, which handles reliable data transfer, and below the presentation layer, which deals with data formatting and encoding. Think of the session layer as the manager of the conversation between applications. The session layer ensures seamless communication between applications by providing mechanisms for dialogue control, synchronization, and error recovery. It allows applications to exchange data in a structured and coordinated way, ensuring smooth and uninterrupted communication. Like, for example, imagine two people having a phone call. The session layer is responsible for setting up the call, managing the conversation flow, and ensuring that both parties can understand each other. So, the session layer utilizes protocols that manage dialogue control, right, and synchronization between applications. Some notable protocols operating at this layer includes, first, NetBIOS, or the Network Basic Input-Output System. And this protocol facilitates communication between applications on a local network. It provides services like name resolution, session establishment, and data exchange, enabling applications to communicate with each other within a specific network. Then you have RPC, or the Remote Procedure Call. RPC allows a program on one computer to execute a procedure on another computer as if it were running locally. This enables distributed applications where different components can run on separate systems and communicate with each other seamlessly. What are the real-world applications? The session layer plays a very important role in various applications, including login sessions for remote servers. When you access a remote server, the session layer manages the connection between your device and the server, allowing you to log in and interact with the server's resources. It can also be used for web applications. So in web applications, the session layer, right, maintains separate requests and sessions for different users. It ensures that your browsing activity and login status are preserved, allowing you to navigate between different pages within the same web application without having to re-authenticate. Now we are on the layer 6, or presentation layer. Let's talk about the concepts involved in layer 6. First is data encryption. The presentation layer is responsible for ensuring secure data transmission by encrypting sensitive information. It utilizes protocols like SSL, or Secure Sockets Layer, and TLS, or Transport Layer Security, to establish secure connection between applications. These protocols use cryptographic algorithms to transform data into an unreadable format, preventing unauthorized access and maintaining data confidentiality. SSL, TLS are essential for protecting sensitive data during online transactions, web browsing, and other internet-based activities. We have data compression. The presentation layer optimizes network performance by compressing data before transmission. Compression reduces the size of data packets, minimizing the time and bandwidth required for transmission. This significantly speeds up data transfer and enhances network efficiency. Now, the presentation layer employs various compression algorithms such as zip, you have gzip, also have deflate, right, to efficiently reduce data size without compromising the data integrity. And the third concept is data translation. The presentation layer ensures interoperability between diverse systems by translating data between different formats. Different applications and systems use different data representations and encoding schemes. The presentation layer acts as a bridge, converting data from one format to another, enabling seamless communication between incompatible systems. And this ensures that data can be exchanged efficiently and accurately between different applications, regardless of their underlying formats. Layer 7, or the application layer. The application layer, which is the top layer of the OSI model, is responsible for providing network services directly to end users. This layer acts as the interface between the network applications and the underlying network infrastructure. It ensures that user applications can communicate seamlessly and exchange data effectively across different networks. The application layer relies on a wide range of protocols to enable various network services. Some common examples include HTTP, or Hypertext Transfer Protocol, for web browsing. We have FTP, File Transfer Protocol, for transferring files between computers, and SMTP, or the Simple Mail Transfer Protocol, for sending and receiving emails. These protocols define the rules and formats for data exchange, ensuring compatibility and interoperability between different operations or applications and systems. The application layer is where users directly interact with network applications. It handles user authentication, ensuring that only authorized users can access network resources. It also manages data privacy, protecting sensitive information during transmission. Moreover, the application layer handles resource allocation, ensuring that resources are shared efficiently among multiple users and applications. Now, the application layer is essential for a wide range of network applications, including web browsing, email, file sharing, online gaming, video conferencing, and more. When you browse the internet, send an email, or download a file, the application layer is actively working behind the scenes and facilitating communication and data exchange between your device and the network. Now, the OSI model isn't just a theoretical concept, it's a practical framework that underpins the design, implementation, and management of modern networks. Its a layered structure provides a systematic approach to understanding how networks function and enabling efficient troubleshooting, protocol development, and network design. Now let's look at the practical applications of the OSI model. First is network design. Network designers leverage the OSI model to create robust and scalable network architectures. Now, by understanding the specific functions and protocols at each layer, they can plan for efficient communication, data flow, and resource allocation. Like, for example, when designing a network for a large organization, the OSI model helps in determining the appropriate physical media, addressing schemes, routing protocols, and security measures for each layer, ensuring seamless and reliable data exchange across the network. Then you have troubleshooting. So when network issues arise, the OSI model provides a structured approach to troubleshooting. By identifying the layer responsible for the issue, network administrators can pinpoint the root cause and apply the appropriate solutions. Like, for example, if data transmission is failing, the issue could be in the physical layer, such as a faulty cable or a loose connection. Alternatively, if communication between two devices is disrupted, the issue might be in the network layer, such as a misconfigured router or a network connectivity problem. Then you have protocol development. The OSI model serves as a blueprint for developing new networking protocols, and by understanding the specific functions and interactions between layers, developers can ensure compatibility and interoperability with existing protocols, promoting a standardized and interconnected networking systems. The model ensures that the new protocols seamlessly integrate with existing network infrastructure, enhancing communication and data exchange across different systems. All right, that's the end of the lesson. In this lesson, we spoke about the OSI reference models and its layers, relevance, and its practical applications. Here, we spoke about details about the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. Thank you very much for watching the video.